Okay, there we go. Let me share the screen. Can you see my slides?
Yes.
Okay. So yeah, this is physics continuing from last week with electricity and magnetism. So last time, session 4 was electrostatics. Now we're looking at capacitors, batteries, and resistors. Do you have any questions about the homework or the content before we start, or do you just want to wait until we go into that?
No questions.
Okay. Oh, people. There we go. Here's an outline of the material. Yeah, I don't want to read over all of that, so we'll just start off here. So I'm going a little bit out of order. This was the order they gave me, but this made more sense to me to start with current. So last week we looked at, or it was not last week, but it was last physics section. We looked at electrostatics, so charges that are in one place and what are the fields they create, what are the forces, what are the potentials, what's the energy. But usually when we care about charge, it's because the charges move. And charges just in space can move, but generally in this, we're going to be talking about charges in a wire moving, and specifically electrons moving. So we define and measure the movement of charge with current. So current is just the rate of movement of charge across something. So across a wire usually, and for this, it'll be across a wire. So here's your formula, but it's, again, pretty self-explanatory. It's rate of movement of charge. So here's the calculus one, dq dt, but for the MCAT, again, you don't have to know calculus for the MCAT. So for the MCAT, you would just have to use this. So if they asked for an average, if they asked for you to find the average current, you could just take the change in current, the change in charge over change in time. A little bit of a tricky thing here, though, is the sign convention. So normally we're going to be looking at electrons moving. You know, positive charges will be protons. Generally, especially in a wire, you know, wires are made out of metals. We have those loosely bound electrons moving, right? Well, however, electrons are negative. So current, the sign convention here is that positive current is actually in the direction of the movement of positive charge. Now, there are no, the positive charges aren't moving, so it's the direction positive charges would move to cause the same effect. So whenever electrons are moving, like in a wire or in a circuit, the current is actually, if we want to draw an arrow for where current is moving, it's actually opposite of that. Unit ampere, which is a coulomb per second. Said last time that 1 coulomb is essentially way too big. So also an amp is an enormous amount of current. Usually you're going to see milliamps or even smaller. Here's just a little picture showing you. So here they have positive charges moving, and that would be the direction of the current. So now looking at resistance. So what is resistance? Well, basically in these wires, in any material that we have, oh, more people. Yeah. In any thing where we have charges moving, we have, hold on one second. Okay. We have charges, current, we also have resistance to that flow. So resistance resists the flow of current. Or you can also, you might hear it say resistance is the obstacle to the flow of current. Yes, any material, even though we think of metals and wires as being conductors, they still have some amount of resistance. Here's the formula for resistance. You do need to know this one. R equals rho L over A. And yeah, resistance is ohms. Rho is called the resistivity. So this is an important distinction here. Resistance is a property of the wire. So the material it's made out of, how long it is, and the cross-sectional area. Rho is actually a material property. So copper has a value for rho. Iron would have a value for rho. You can look these up in tables, of course. This will be provided for you on the MCAT if you need to do any calculations. And yeah, it's low in conductors and high in insulators. That makes sense, right? Insulators resist the flow of current more than conductors, so R has to be higher, so rho is higher to make it higher. You might also hear of the conductivity. Resistivity is just the inverse of conductivity. And then another good fact to know here is that there is a temperature effect here. So really what's important to know is that these values can change with temperature. So resistance and resistivity. Well, resistivity changes, which then changes resistance. But in a conductor, so in a metal, it actually increases with increased temperature. Quick practice question here.
I have a question.
Go ahead.
About the formula. L, what is L and A? Is it length and area?
All right, we got a question. What are the units? And yes, so L is the length of what you're looking at. So like let's say that this piece here is what we wanted to find the resistance of. L is the length and A is the cross-sectional area.
Okay.
Units. The units are whatever units make this whatever units would have everything cancel out. So typically, if you just use SI units for everything, you can't go wrong. So if you just do L in meters, A in meters, look at what units rho has, and it should give you ohms when you cross everything out. The important thing, though, definitely is you need to keep the same unit on these. So you might be given them in like millimeters, but you would need to rewrite those as meters. Again, depending on what the unit is for rho. Does that make sense?
Yes.
Yes.
Okay. Quick practice question here. So if I have an extension cord and I want the extension cord, you'd want to have negligible resistance. So which of the following would help us have that cord have lower resistance? There are multiple right answers here. Thick cord. Okay, any more? So remember the equation, resistance is resistivity times length divided by area.
Decrease the temperature.
All right. So you're both right, but there's one more here. So remember, it's rho L over A. So the longer the cable is, the more total resistance we have between the wall and between what we care about. So if we don't want this thing heating up and we don't want it to use up, have a massive voltage drop over this cable, we don't want to use a super long cable. And then you were right on the other one. So thick cord decreases resistance, and then for a metal, which it's a cable made out of metal, decreasing the temperature decreases the resistivity, which then decreases the resistance. Question here. So if the cross-sectional diameter of a wire, if we double that diameter, what happens to the resistivity of that wire? Any guesses?
Decreases by a factor of 4.
All right, we have increases by 2, decreases by 4. It actually does not change. So the question said resistivity. Remember, resistivity is rho. So resistance equals resistivity times length over area. Resistivity is a material property. So it doesn't depend on how we shape the material. It depends on things like temperature, but the length and area do not affect that. So now that I'm done tricking you, here's what you were trying to answer. What happens to the resistance of the wire? Someone had it. You said it before. For this one, it decreases by a factor of 4. So if we remember, diameter is proportional to area is proportional to diameter squared. So if we increase, we double it, we quadruple the area, so we decrease by 4. What if we rearrange? You mean rearrange the rho L over A equation?
Yes, that's what I was thinking.
Well, the problem with that is that resistance is the thing that changes. Resistivity is a fixed value at constant environmental conditions. So yes, you could solve, and you could theoretically be asked to do that. We could say, okay, I'm going to give you R, A, and L. What's rho? However, understand that rho never depends on how we shape the material. That's what R depends on the material, which rho is telling you a fact about the material, and then it depends on how we shape the material, which is L and A. Does that make sense?
Yes.
Okay. So now voltage. So we talked about voltage, which we called potential difference at first with electrostatics. So just like how if we have point charges in space, we have potential associated with that. If we pick points along wires in a circuit, we have an associated voltage. And we do that relative to a starting point. So typically, if we look at this little circuit where we have the battery, we might say that this part down here, we can set that. Remember, voltage is relative. Potential difference is relative to a 0 point. We may set that as our 0 point, and then say these points along the circuit have a certain voltage. But we also talk about the potential difference or the voltage drop across individual components. So I look at the one side of a resistor and the other side of the resistor, one side of the battery, other side of the battery. And different components can either increase or decrease voltage as we move across them, as this current, these electrons move across it. So if we're looking at batteries, as we move across, remember, with the sign convention we use, the current comes out of the positive end. So as we move across this battery, we're actually increasing the voltage, which is the purpose of a battery. And if we had a charged capacitor, which we'll see more in a minute, if we charge a capacitor, then we will, if we put it in a circuit, the voltage increases as you move across it. However, resistors, this should say charging capacitors. Resistors or a capacitor that we're charging with a battery or an inductor, which we don't really care about inductors for the MCAT, but I put it here just for completeness. Those drop the voltage. So if we look at this circuit, it's conservation of energy, and you'll see more whenever we go into circuits in more detail in a future unit. But this battery increased the voltage. So as these electrons go over this resistor, there is a voltage drop. And this equation, which hopefully a lot of you are already familiar with, V equals IR. This is telling you the voltage drop across a resistor, current times resistance. So we can also phrase it as the current over a resistor is proportional to the voltage drop. And the constant of proportionality is this resistance. And then capacitors and inductors gets a little more complicated because they also have equations that tell you the voltage drop. And of course, this tells you the current as well if you just divide by R. But they're more complicated because it's actually time varying. So you're not really responsible for those for the MCAT. Resistors in combination. So I'm just starting out here. And I will say, typically the MCAT the MCAT likes to ask things in biological context. So if you see circuits and electricity on the MCAT, typically it will be some sort of biological application. So we can actually model biological systems using as resistors and capacitors. And you may see something presented like that on the MCAT, but you would just do the math the same way. And also, devices like light bulbs. If you see a light bulb in a circuit, you often will model it as a resistor, which makes sense, right? A light bulb is taking in energy. A resistor is just wasting energy as a, if you think like a little resistor you put in a circuit, it's just wasting the energy as heat. A light bulb is using it, but it still has a resistance value. So this is just to show you what series and parallel means. Series means they're one after another like this. Parallel, note the multiple branches. So you think of it like branches. These are all in one branch. These are all split. And you can mix and match these as well. But what happens when they're in series and parallel? So in series, to find the total resistance, so the resistance from one end to the other, you just add them up. In parallel, it's a little bit different. You have to use this equation here. You take the inverses and add, and then you take the inverse of that. You do need to know, I think, basically all of this on this slide, but there aren't really equations for these other ones. So in series, the current is the same passing through each resistor, which is just a conservation of mass thing, right? If the electrons come in, the electrons have to come out. So the current is the same across all of these. In parallel, the current splits because the current splits into each of these branches and then adds back up here. And the larger resistor gets less current, which makes sense, right? Resistors resist the flow of current. For voltage, the voltage here adds up. You have to add the voltages to get the total voltage drop. For these, the voltage is actually the same across each of these. So R1, R2, R3, R4. And as a consequence, remember V equals IR, so we can do IR1 equals IR2, or I1, R1 is I2, R2, I3, R3, I4, R4. And that's also a consequence of conservation of energy, because any path, basically any path you take on the circuit, you have to have the same voltage drop. And you'll see more of that when we go into the circuit laws next time. So here's a quick practice question. Pardon the drawing I made here. So I have this circuit with one resistor. I want to make a new circuit that has two resistors they have the same value. And I want these circuits to have the same total resistance. So what resistors? R2 has what relation to this R here? Hopefully this problem setup makes sense. Let me know if it doesn't.
It's double.
That is correct. So actually, I skipped over it, but on this slide, I mentioned that when resistors are in parallel, the total resistance is actually always less than any other resistors. And there's actually a shortcut. If the resistors are in parallel, if they're all the same, you just divide by the total number of resistors. You can do that formula there too. But let's say this was 10 ohms. If these are both 20, you just take 20 and divide by the number there are 2, and that's the total resistance, which is the same as this. Batteries. So circuits that you see on the MCAT are typically going to be DC circuits with a constant voltage, not time varying. And we usually use batteries. So batteries create an electromotive force, which is essentially a voltage. So it creates a potential difference over it. So it creates a voltage gain, you can just say. So from minus to positive. Ideal battery, which you're most common to see, has no internal resistance. So the resistances in the circuit are just some other resistance. the other resistors you have. However, a real battery always has some sort of internal resistance. Remember, any wire, any piece of metal has some resistance. So it makes sense that a battery would as well. And we model it like this. We put a resistor inside. Think of this box as being the battery. We put the voltage gain, and then we're going to have a small drop over this resistor, which, of course, is IR. So quick question with that. So if we have one of these non-ideal batteries with an internal resistance, the total voltage drop, so the total voltage drop across this box, is that going to change depending on what else I have in the rest of the circuit? True or false? I'll show the answer for this one. This one is true. So remember, the total voltage drop is this equation here. The voltage gain here minus IR. Well, depending on the total resistance of the circuit is going to change that current, which is then going to change the value of IR and change the voltage drop. So that's true. That's it for resistors. Now for capacitors, which, again, these have a lot of medical applications, which you'll see in the practice passage, and you'll also see in MCAT questions. So the point of a capacitor is to store charge. Batteries also store charge, but batteries use a chemical reaction. Batteries store voltage through a chemical reaction, and they're designed for long-term storage. So the voltage of a capacitor, or the voltage of a battery, does not change very much as you use it. A capacitor stores voltage as charge across plates, and it's designed to quickly charge and quickly discharge, relatively quickly compared to a battery. Capacitors have what's called a capacitance, which is the charge they store per unit voltage. So here's an equation you need to know. Again, that's the definition. So capacitance C equals charge Q divided by voltage V. Unit is a farad. Here's another one you might see. It's just this equation rearranged. Q equals CV. So capacitance is a property of the capacitance does not change based on the circuit. Capacitance is based on the materials. We'll see how the material affects it in a minute, and it depends on how we shape the materials. So look at these capacitors I have here. They're all some of them are cylindrical. Some of them are like these flat circles, which are going to have parallel plates. So that affects it. So the shape, cylindrical versus flat, and then how spaced out the plates are inside is going to affect this capacitance value here. But the voltages in the rest of the circuit, how we put it in a circuit, does not affect capacitance. So for the same capacitor, if we charge the capacitor to a higher voltage, we're never going to change C. We're going to change B, which then changes Q. So more voltage equals more charge. Electric field. So remember I said that capacitors work by putting charge on plates that are very, very close together but still separated apart. So you can see at this picture here, I have this battery, and then I put this in the circuit, the capacitor. So remember, the electrons are actually coming out of the minus end here. So the electrons come out of the minus end of this battery, and we're putting electrons on this plate of the capacitor, which is then causing, and we're pulling electrons away from the positive end and creating a positive plate here. So the simplest capacitor is called a parallel plate capacitor. It's literally just two plates that are very close together but not touching, which is why capacitors are usually shown like this with the two lines. So remember from before that charges create electric fields. And between plates, so you can see the picture here, we showed this distribution last time. Between parallel plates that we assume the plates are infinitely long because they're very close together. So compared to how close together they are, they're very long. And so the field in between them is a constant. And remember that for a constant field, we have this equation. Voltage equals field times the distance, which is from last time, but that's one you need to know. And then for a parallel plate capacitor, we can calculate that capacitance. So remember, if we know Q and V, we get capacitance from this definition. But for a parallel plate capacitor, you use this equation. Epsilon naught A over D. Epsilon naught is just a constant, 8.85 times 10 to the negative 12. That will probably be given to you. And then the area of one of the plates and how far spread apart they are. So practice question. If a capacitor is held at a constant voltage, so I'm keeping V a constant, will it store more charge if I move the plates further apart? Yes or no?
False.
What do you mean by both?
No, I'm sorry. I said false.
False. Yes, that is correct. Because remember, C equals constant times A over D. So if we increase the distance, capacitance drops. And then go back here, Q equals CV. If V is the same and C drops, then Q also drops. Energy storage. So remember from before that voltage is a measure of potential where it's the potential energy per unit charge. So from that definition, we can get this equation here. And I'd say this one's the most important to know. The energy in a capacitor is 1/2 CV squared. So when you charge a capacitor, the voltage on the capacitor goes up and the potential energy increases. And when it discharges, you lose the potential energy. And it is converting into kinetic energy because we're using the energy stored in the capacitor to move electrons out of it when we're discharging it.
So energy stored in a capacitor is U?
Yeah, U is just a generic symbol for potential energy. You could also call it capital PE. But U is fairly common. I think I've seen that on the MCAT. So dielectric. So we said that the capacitance depends on how we shape the material and the material properties. The shape, I showed you that parallel plate equation, but typically capacitors are not going to have air in between the plates. We're going to put an insulating material in between the plates. And for somewhat non-intuitive reasons, that actually increases the capacitance. You can see here the reason why. The specific reason is really not important here, but essentially it creates an opposing electric field and decreases the electric field within the capacitor, which in turn decreases the voltage. But if we're storing more charge at a lower voltage, that means it has a greater capacitance. So dielectrics have a constant kappa. It's not K, it's this, the funny looking K. That is a material property. Again, it's also, you can look it up in tables. There's a value for air, rubber, glass. For air, K is very close to 1, which is why beforehand I gave you this equation. I didn't put the dielectric constant, but if we just have parallel plates separated by air, we can ignore it. Oh, there we go. So if you're asked questions about this, it's important to know the difference about when is charge the same and when is voltage the same. So they might ask you to compare a capacitor with and without a dielectric, or they may say, okay, we're going to put a dielectric in between this capacitor while it's charged. What happens? So if we have a capacitor in a circuit, the voltage can't change because we're fixed to the voltage of that battery. So if you add a dielectric, we will actually remember the dielectric increases the capacitance. The voltage will actually drop, but then the battery will charge it back up again. So the voltage will stay the same, but the charge will increase because remember, capacitance increased and Q equals CV. But if it's just out in space, if it's not connected to anything, there's nowhere for the charge to go. So the charge can't go anywhere. So that means that the charge doesn't change, but the voltage decreases because remember, that's due to the field decreasing from here. And again, Q equals CV. And there's actually an equation for this too. So if you're in a constant charge condition, you just divide out the kappa, and that gives you the voltage. But you can derive that. You could just plug into this equation, and then your Q equals CV, and you would get that answer as well. Capacitors in combination. This is actually the reverse of the resistor trend. So I'll actually start off with in parallel. It's down here. So capacitors in parallel, it's like resistors in series. You add them up. So it's a bigger capacitor. And that makes sense intuitively because you can think of it as being like think of if you were to kind of smush all those together, you'd have a capacitor with a larger surface area, which from that equation would increase the capacitance. Remember, anything in parallel, voltage has to be the same, but the charge will be split. And there'll be more charge on larger capacitors. Because remember Q equals CV, larger capacitor stores more charge at the same voltage. In series, it's this inverse thing, and so it's actually going to be lower. This is a little bit less intuitive, but this is really all you need import. You just need to know the rule for the MCAT, but if you're curious, there are some videos online that explain this really well, why this is the case intuitively. In series, the charge on each capacitor is the same, and the voltage will be split. You could use Q equals CV to find the voltage, and the voltage is going to be higher on the smaller capacitors. Okay, we have actually quite a bit of time. So do you all have any questions before we do the practice passage? Type or talk?
No, did you have a picture of capacitors in series and in parallel? Was it the previous slide? I think I missed.
Let me go back to the resistors. I did not put one for capacitors. Just pretend these are capacitors.
Oh, but it's the same thing?
It's the same rule. You can talk about any component being in series and parallel. You can actually have batteries in series, and you just add up the voltages. And if we were covering inductors, you can have inductors in series and parallel. Same definitions of series and parallel. It's just the equations are opposite for resistor versus capacitor.
Okay.
Can you explain like what you were talking about in terms of like when a capacitor is added, the charge decreases or the voltage? Like I didn't really quite understand that. Can you explain that again?
Sorry, which slide was I on for that? Was that this?
I think the previous one.
This?
I believe so.
The dielectric?
Yeah.
Why does the voltage decrease?
Yeah.
Okay. So this is trying to explain, this might be a little bit beyond the scope here. So the dielectric is an insulating material we're placing in between the plates, okay?
Yeah.
The reason is a little bit complicated, but essentially what you need to know is that the dielectric creates, remember, capacitor plates have an electric field. That's this E0 from the plus to the minus. The dielectric within it actually has an opposing electric field.
Okay.
And we add those up, that means the total field is smaller. Does that make sense?
Mm-hmm.
Okay. Now for parallel plates, V equals ED. Voltage equals field times distance. Well, distance didn't change, but we just decreased the total field. So if we decrease the field, we decrease the voltage.
Okay, got it.
This is for the same, if we're assuming that Q stays the same,
Mm-hmm.
then the voltage decreases. But remember, Q equals CV. So if we're keeping the same charge at a lower voltage, that means capacitance is increased.
Got it. Thank you.
Yep. Anything else? All right. here's the passage. So I'm going to stop sharing and give you that link. Let me know if this doesn't work for anyone. So as usual, take about 15 minutes on that. Since there's just a few of you, you can just let me know when you're done, and then we'll go over the answers for that. And if you have any questions or need a hint, I can give you that as well.
Thank you.
All right, I've got one done. Are the rest of you finished? It's fine if you're not.
No, like 3 more minutes.
Okay. All right, is everyone finished now?
Yeah.
All right, let me share the screen again. I'll pull up the passage. Okay, can you see the screen now? Hopefully. Okay, so
Yeah.
question 1, if you were to add an additional 3 times 10 to the negative 6, 3 microfarad capacitor in parallel with the original, what would be the equivalent? That's those series and parallel combinations we're talking about. So you just add if it's in parallel. So 3 microfarad plus 1 microfarad equals 4 microfarad. How much energy is stored when it's fully charged? Remember the equation for energy, 1/2 CV squared. There are several equations, but that's the best. Usually the easiest one is to use is going to be 1/2 CV squared, which we were given the capacitance and we were given the voltage of charge. You plug them in and you get 8.
So I got, for this one, I got 32. I think I did 1/2. C was it 4 times 10 to the negative 6 times 4,000 squared?
So you were looking at question 1. We're back to the original 10 to the minus 6.
Oh, so you just had to use 10 to the minus 6. You didn't.
Yeah,
Oh, okay.
the questions are all isolated from each other. So
Okay.
if they wanted you to use this, they would have said they would have said something like, okay, we're going to replace the capacitor with the system from question 1. But
Okay.
they're just
Okay.
talking
I
about
mean, I picked 8 because it was the closest to 32, but now I know that, so I probably would have got 8 if I would have used 10 to the negative 6.
Yeah, you did the math right because you got 4 times higher. You got a 4-time higher answer. Increase the separation between the plates while hooked up to the voltage source. Well, it already tells you it'll decrease the charge. But why does that happen? Well, okay, let's think what's happening here. So let's say it's parallel plate, but even if it's not parallel plate, it may be, 2 cylindrical sheets. No matter, increasing the distance is always going to linearly decrease the capacitance. But we use that epsilon naught A over D in the case of parallel plates. But the point is, if the plates are further apart, C decreases. Hooked up to a voltage source, that's trying to tell you that the voltage is constant. So Q equals CV. So C is less times constant V decreases charge. But the answer just asked decreases the capacitance. Again, epsilon naught A over D. How much charge is stored when it's fully charged? That's Q equals CV. So we were given C and we were given V. And again, you're not using that bigger capacitor.
Q is charge and C is capacitance.
Correct. And I is current, R is resistance, V is voltage. Sometimes you'll see lowercase q for charge as well, because Q is a whole bunch of stuff. But if it's an electricity problem, Q is charge.
So it's Q equals CV.
Yeah. The starting equation, typically books will start off with C equals Q over V. That's just a definition. We define capacitance as being the charge per unit voltage. But a lot of times that's just rearranged, right? Cross multiply, you get Q equals CV.
Okay.
All right, this is just like the last one. If we connect an additional 10 to the negative 6 in series, what will be the equivalent? So you can use that formula, but remember I told you that for resistors in parallel, you can just divide by the number of resistors if they're all the same. So for capacitors in series, you do the same thing. So you just take 10, since they're equivalent, you just take 10 to the negative 6 and divide by 2, and it's 0.5 times 10 to the negative 6. Also remind you that you don't have a calculator on the MCAT. So if any of the math was a bit of a trouble, you might need to review just like arithmetic, because you do need to be able to do these quickly without a calculator. But notice the answers were pretty spread out. So these gave you nice numbers, but even when you have to do things like square roots and exponents, you typically can just ballpark it and use nice numbers that are close, and you'll get one of these answers. All right, here's the slide again. Just again, you can email your questions there, and if you like what we're doing, you can donate there. Are there any final questions? I can stay on for a little bit after 9.
No, this was great. Thank you.
Yep. Anything else? All right. There are office hours this week as well. I'm not hosting those, but I'm sure the other tutor can answer your questions.